Hi, everyone. My name is Nicholas Lane, and welcome to Flower Monthly July. We have, as usual, a jam-packed Flower Monthly session for you. So thank you for those who are joining live, and perhaps those who decided to join later via our YouTube channel. I'm just going to get things underway for Flower Monthly July and show you the agenda. So our agenda is as follows. We have a very sort of brief flower update that'll go for about 10 minutes, tell you a few of the things that have been going on in the past month. And then we're going to transition to two very special invited guests. We have Dr. Siba Haidar from ESIEA, and she is going to be talking to us about her research that is investigating how you can build federated models of violence detection. So, a very important and timely problem for us all to sort of make progress on. And she's going to be telling us about how this work has been done in a federated manner that many of you, I think, will be quite interested in. Um, After her presentation, we will hear from Adway. He is at the University of Maryland, and he has also been a part of the uh, the Flower Pilot program. And the work that he's been doing focuses on how do you perform image segmentation using privacy-preserving techniques. So fantastic. Um, but before we get to these two really important talks, let's take a look at what has happened in Flower in the last 30 days. So let's look at some of the highlights. One of the highlights that we're very proud of is that Daniel Abuyoto, who is the co-creator of the Flower framework, has been awarded um, one of the Rise 25 honorary collections that have been designated by Mozilla. And so this is a very important award that's awarded to a variety of folks out there worldwide who are making a really important contribution in various fields, mostly related to the world of open source. He has been awarded this honorary status under the category of entrepreneur kind of accomplishments. And in fact, there will be an award ceremony in August 13th in Dublin. And so congratulations to Daniel. Very cool. Good stuff. Um, if you want to read more about this, you can take a look at this URL here that's listed at mozilla.org. And so you can see all the other folks who've been assigned this award as well. So it's really great. Um, if you are working in particular in the machine learning field, one of the major conferences of the year is ICML. And so we thought it was appropriate to just signal that we're going to send two of our research scientists to ICML. This will be taking place in about 3 weeks from now in Vienna, Austria. And so many of you have seen the work done by Jan Gao and Mohammed Nasiri. They're both research scientists working at Flower Labs. They work on different parts of the Flower framework, and so you've often been seeing contributions from them. You can meet them at this conference in a 3 weeks' time, and they'll be attending many of the sessions. And just feel free; they're friendly folks. Say hi to them when you're there. They'd love to talk to you about your ideas in the world of federated learning. Uh, on this note, um, later in the year at KDD, so a conference that's more focused on actually a wide footprint of data science innovations. We're also going to hold a hands-on tutorial for those of you who are interested in learning more how you can perform various kinds of privacy-preserving machine learning, and in particularly those who might be wondering how you can get the most out of the Flower framework. If you go to KDD this year, it'll be held in Barcelona, Spain. And on the Thursday, the 29th, so it's a multi-day event, but on the actual Thursday, we will be running this hands-on tutorial. And if you attend this event, you'll be able to meet not only Mohammed, not only Jan, but also Han Peng and Javier Fernandez. All of these four folks will be providing this hands-on tutorial, and they'll be at different events of KDD. You can reach out and chat to them, or attend the tutorial and sort of dive in to see how you can get the most out of flower. That's great too. Next, we wanted to highlight just recently, and this is a piece of work that came out it came out in the last couple of weeks in terms of archive and being sort of hitting the news. It was a really interesting study that examined a variety of FL frameworks. And of course, there's a number of different ways that you can produce and conduct federated learning out there. This systematic study that was done by a variety of scientists and researchers at different institutions in Germany. They systematically looked at the different capabilities of frameworks out there. And of course, many of these frameworks have different strengths and weaknesses. But across the board, they found using this comprehensive approach to measuring the different capabilities of these frameworks that Flower came out on top. And so we work very hard on Flower, and we really want to make it the best framework for you all to use and work with you to improve it continuously. And so we're very heartened to see this result. And of course, the other frameworks too also have, their other comparative strengths. But it's wonderful to see that Flower came up on top from this independent review of different frameworks. It was really great to see. The final piece of news is perhaps maybe the biggest out of all of them. We released in the last month Flower 1.9. And so Flower 1.9 provides a lot of features that people have been working hard on in the community, a lot of features that folks have been requesting that we've been trying to deliver and have ready for usage. And so Flower 1.9 it really is a really pretty big step forward. What I've listed here is just the highlights, really. So things like built-in authentication has been an important enabler for certain types of production deployments that we see out there, as is end-to-end Docker support. And so as part of 1.9, Docker support is quite a bit more hardened and made compatible with various types of components of Flower, such as the superlink, the supernode, and server app aspects of it. You might remember we had a deep dive into Docker support for Flower back in Flower Monthly June, and now in Flower 1.9, this Docker support is right there waiting for you. Other aspects include some pretty significant advances in the simulation engine. We also have a brand new baseline that was contributed by Huawei. This is a baseline that relates to performing LLMs and fine tuning. It was actually featured in last month's Flower Monthly as well. So if you're curious about this particular baseline, feel free to check out last month's recording. And then other aspects you'll find there kind of run across the board, including improved new templates for MLX, so Apple's ML acceleration that works so well with their hardware. You'll find these templates existing for transformers, scikit-learn, and TensorFlow. And so then they are also some really significant usability advances in 1.9 as well. And that is just a tiny sampling of what's available. If you want to learn more, I recommend actually the first place you should head to is Flower Discuss. It is a recently released capability that you'll find on the Flower Framework website. There you'll see a lot of different types of questions that are being answered by both us and the community. And so we have a special Flower Discuss entry just for 1.9 there. If you want to sort of see a more conventional view of this material, you can check out a blog article that was also released back when 1.9 went live. I'd also tease that subsequent Flower versions are really close to being ready, and so you'll really be able to enjoy some even more further advances in the coming weeks and shorter. So that was a sort of a whirlwind tour of what has happened in the world of Flower over the last month. Without further ado, let's move now to our invited speakers for Flower Monthly this time around. And so it's with great pleasure, I'd like to introduce Dr. Siba Haidar. She is at the Graduate School of Engineering at ESIEA and has been working for quite some time in this sort of general area of how do we perform machine learning-based detection of violence within video and that type of modality. It's obviously an important topic. And I recently ran into her work when looking at her LinkedIn posts that were describing the advances she's made in this domain, but with respect to federated learning. And so I thought it would be great for her to share her work, her findings, understandings, and so forth with you all. And so she was kind enough to come to this event and provide us with a great little presentation here. So over to you. We're delighted to have you here and really curious to see what you've been working on.
Thank you, Nick. Thank you for the nice introduction. So I think I have to share my screen now.
Sure, yes, please.
Okay. Okay, so let me begin by good afternoon, everyone. Thanks for inviting me. My name is Siba Haidar. I'm an associate professor at the CUA, which is an engineering private school in Paris. So I will be presenting our research on balancing accuracy and training time in FL for violence detection in surveillance video. So let's begin. To introduce myself, I have a PhD since 2005. I have over 20 years of experience in higher education, and my specialization is from the beginning video analysis and recently machine learning. So my current research should focus on intelligent and effective tutoring systems, and parallel with my initial subject of research, which is video analysis and personalized federated learning for violence detection recently. So without waiting, let us begin by the problem. What is to be solved? We have to solve this. So our primary goal is, as you can see, violence somewhere, and a surveillance camera that is surveying this violence. So our primary goal is to enhance the detection of violence in surveillance videos while aiming to improve both accuracy and efficiency while preserving, of course, data privacy. So we want accurate system. We want efficient system because if the man dies, it's a little bit too late. And of course, since this is the surveillance cameras, this is very private data. We don't want to go transporting it everywhere. So let us begin. The objective. Our objective is to propose a deep learning architecture that provides privacy, preserving real-time or near real-time adaptable and resource-efficient models. We don't want our machines to be over calculating themselves. And of course, everybody agrees with me that real-time violence detection can alert authorities immediately. This is our dream, and allowing for swift intervention and increased public safety. So the benefits are clear. In a more realistic scenario, we can imagine the city with numerous surveillance cameras all around the city corners and many CCTV centers. So each camera is linked somehow to a CCTV center, so there are also numerous CCTV centers. As you can see in my simple schema, each camera will collect data and send it to a central server, which can lead, of course, to server overload and privacy concerns. Obvious, the intervention. So FL here is a good solution that allows local data processing in each center, addressing these issues and ensuring efficient real-time violence detection while maintaining data privacy. So why this research matter? Again, I'm repeating myself. It's ubiquity of violence detection. We need that everywhere, and FL is a good solution. I will be presenting the rest of my talk around three focal points. The first is our publication that was recently accepted in the Journal of Computer Science and Technology. The second is a new publication under review, still under review. And I will conclude with what is our contribution so far. Of course, every study I'm not alone. We are a team, so I have colleagues and students working with me. So let us begin. This research has been published in the GCST, which is a very known journal, and this demonstrates the significance and the credibility of our findings. What we are most proud of is that we are dealing with video data. Video data is a little studies in video data and federated learning are still few. So we are very proud of our contribution. So as we have said in the introduction, federated learning will work in our case, obviously, because we have local training, we have privacy preservance, and it can deal with heterogeneous data. And so naturally, the solution is comply with GDPR regulations. And this is a solution where other classical machine learning and deep learning fail. So federated learning workflow, as we all know, is the following. We initialize a global model, we distribute it to devices for local training, we aggregate updates into the new global model, and we repeat the process until the model converges. In order to present you our methodology, we wanted to develop a method that works independently of the violence type. We know that there are different types of violence, and violence in soccer field is not the same as violence in banks, is not the same as violence in the street, and so on. So we wanted to develop a model that is independent of this, and for this we chose our datasets ahead. The datasets are all published, and they are convenient for comparison because we have study on them. As we can see, we have Hockey Fight dataset, RWF 2000 dataset, Crowd Violence, and Air Club. I highlighted the two middle datasets because more than one experiment was used these two datasets in comparison to the four others. So now quickly we will show you our proposed method. This is a compilation of other interesting methods in the literature on which we added our contribution. So it consists of multi-input models together with a convolutional 3D layers for feature extraction, of course, because this is a 3D input data. This is a video data, followed with some together with the transfer learning. So we don't initialize our weights from zero. We initialize them based on a transfer pre-trained weights on large data set, which is 41M. And then we follow this by fully connected layers for classification purposes. So steps 2, 3, and 4 are based on an existing work, which is Ternani and al. Very interesting work. We added to this the multi-input models. I will talk about this later. And of course, we opted to accomplish the one-cycle method consisting of applying a single cycle of cyclic learning with a high maximum learning rate, which will permit us to achieve super conversions. So this is the model architecture. As of the architectural variants, you know what is gating mechanism in neural network. So gating mechanism was used in Chang and al. Publication on RWF dataset. It consists not only of feeding the model with the video input, but also with another input, which is the optical flow. What is the optical flow? The optical flow architecture uses the optical flow to estimate motion between consecutive video frame. It's like difference between consecutive video frame, but it includes also the direction. The optical flow includes the nature of the movement and the direction of the movement. So Cheng and al used this multi-input in their models and accomplish good accuracy in motion and violence detection. We proposed, so we asked the question, why don't we use the simple difference between frames, and what is the difference in accuracy when we do so? So we proposed the diff-gated. So as I call their method the flow-gated architecture, we proposed the diff-gated architecture, which is a simple frame difference. And we will show you the results. So along with this multi-input models, they will we do later the temporal pruning before the merging block and the fully connected layer. So this is the idea in our model. We have the 3D convolutional layers. We have the transfer learning. We have the fully connected layers, but before that we have multiple inputs. Sometimes we tested flow-gated, sometimes we tested diff-gated, and we accomplish super conversions. For the first series of results, of course, we asked ourselves the classical question, what if the classic classifiers accomplish the work? So we tested SVM, decision trees, random forest to do the classification violent, non-violent scenes. As you can see, the accuracy is acceptable, giving the SVM the highest accuracy rate. The training time is acceptable, but you have not to forget the 5 minutes that are needed to extract the features in order to feed them to these classifiers, which makes this solution not acceptable anymore. It is not efficient. It is accurate, but not efficient. So that's the answer for our question, why do we have to go to the machine learning solution, the deep learning solution? So in deep learning solution, of course, there is dataset pre-processing time because there is no feature extraction. Feature extraction will be accomplished inside the convolutional layers. Okay. But the pre-processing time is very acceptable, 210 seconds for a whole data set of 350 videos and so on. So this is to show you the pre-processing time that were consumed in order to prepare our dataset to feed the model. As a baseline to our proposed architecture, we calculated the same metrics for the Cernani and al. Architecture, which to recall, they do not use superconversion. They do use convolutional 3D, but they do not use superconversion. And they do use early stopping, sorry, and they have these results for each of the data set. By comparison, we show you our model, which was trained with superconversions and a high learning rate, achieved high accuracy and efficiency, make it ideal for real-time violence detection. So I will go back to let you see the difference in training time. Maybe the accuracy dropped a little bit by reference to Cernani and al, but in comparison with the efficiency, we gained. Our aim is to provide accurate but also near real-time classification. So this is our this is where we have a good point here. And next, we tested the proposed diff-gated in comparison with Cheng and al's flow-gated architecture. As you can see, we gained in time, so in processing time for a video, it was 9 seconds by Cheng and al. We reached a fraction of a second for the same video in average, and we gained in accuracy. So it was very obvious that the diff-gated model outperforms the flow-gated model in both accuracy and processing time, highlighting the benefits of our proposed approach. So all of this was in centralized learning. There is no federated learning yet. Now we will be talking about federated learning. All what we did is to propose an efficient model in order to export it to FL. So next, we explored our model on the federated learning as a first step, which led to our first publication. And the algorithm used was a federated average. We experimented with both TensorFlow and Flower framework, but unfortunately, with TensorFlow Fed average, we didn't succeed to converge. With Flower framework, we converged using 2 clients and a totally balanced distribution, and we reached the accuracy of 97.72% starting from round 2. First of all, the good news is that we reached convergence, and we can proceed to the next. So this was the result and contribution in our first study, and it proved that FL is a good solution in the subject. So as an accuracy, this is a summary of our result. Accuracy improved, training time reduced, FL demonstrated, but the limitation was that the effort were limited. We could not use more than 2 clients. We could not use non-IRD data. So back to our outline, I reached the second point of my presentation, and now you will be, for the Flower community, offered an avant-premiere. Here is a submitted new research work on which we worked this year, and which is currently under revision in a prominent federated learning conference. We have high hopes for its recognition and impact. So in this work, we explored personalized federated learning. We searched for the answer, how would we do to continue to succeed with more than one client with non-IID data. And we explored with personalized federated learning architecture for violence detection and surveillance video. So why the shifting from FL to PFL? The answer is clear. You can see here we have surveillance camera everywhere in the cities, the schools, the transport, retail, hospitals, residents. There are different kinds. You cannot expect that they all have the same amount of data, the same balance between violent and non-violent video, and so on. This is non-realistic. And because our previous study only converged with a perfectly balanced data. So this is the why. And between the proposed and studied methods for personalized federated, we chose the FED pair. The FED pair, I put the QR code here. The community is very familiar with this because of many reasons. They demonstrated theoretical advancement, and they have a very well updated GitHub repository on the Flower framework. So the use of this was really very convenient for us. It applies theoretically and it is available, so we can use it. So we just have the opportunity and use this repository. Of course, they use a different model. They experimented with ResNet and MobileNet. The paper is about Flickr and NIST datasets, which are images. So, of course, we did the customization, we changed what we had to change, we implemented our model, the 3D conv model, and we adapted starting from this FED pair, the personalized federated learning, whose flow is, as you can all know, to initialize a base and personalized layer weights. So not only a base weights, but also for personalized layer weights, distributes these weights on the devices, perform local training while updating personalized layer, and then aggregate the base layer and iterate until this converges. What is the difference? The difference is a fine-tuning in the personalized layers, special for each client, permitting for each client to adapt to its special context. So long story short, this is our architecture. Here is the split. Before the decision layer, we have the fully connected blocks, and we have the parameter decoupling just after the convolution blocks. So again, we have the base video. We pre-process this video in order to have the same color system, the same resolution, etc. We divide them into equal video chunks. And then in our architecture dedicated model, we implement the personal federated learning. To finish, I will show you 3 experiments on PFL on violence dataset. The first, we kept a balanced dataset with the same number of violence and non-violence classes for each client. And the second, we vary the number of violence and non-violence classes for each of the clients on the RWF. And in the third, we added the crowd violence dataset in order to add the heterogeneity of the data. And the happy results are like this. For the first balanced dataset, We have 900 samples of fight or violent and non-fight or non-violent samples for 2 clients or only, and we have reached an accuracy of 98.69%. And this validates the model accuracy. Everything is going well so far, so well, just like FL. In the unbalanced data set, we understand more the model performance when classes are uneven and samples are unevenly distributed across clients. We used 3 clients. We managed to increase the number of clients in the personalized federated learning, and we reached a good accuracy, which is the same as the previous balanced test. In the third combined test, in which we added another set of videos from the crowd violence dataset, we managed to do the training with 4 clients, and we reached a very happy accuracy of 99.3%. So this could not be better. This is a summary of the results. I have nothing more to say. I conclude with the following. We managed with the personalized federated learning to increase the number of clients, things we could not do before in the previous paper. We improved accuracy. We managed the heterogeneity of the data. We succeeded to train and to converge with non-IID data. And we solved a memory issue because in the previous set of experiments, we had a little problem with the memory freeing after each cycle, and this was resolved also in the PFL. So we achieved significant improvement in accuracy and efficiency for violence detection using FL and PFL, using datasets like RWF and crowd violence. And for the future directions, I'm happy to be here. Maybe we can discuss collaboration, PhD thesis. Our next focus is to go back to our original interest, and not only to classify violent, non-violent scenes. We will be interested to have more detail. What kind of violence is this? Because we all know that there is also non-physical types of violence. There are also verbal violence, etc. So we would move to the next step, which is scene description, if we can say. So that's it for me. I'm very thankful for your listening and your attention, and maybe, and I am very interested in your question. Thank you.
Thanks so much. Wonderful talk. And yeah, I'm sure there's a lot of people here who haven't seen this particular application done with FL before. Let's see, I'll go to the Slack, I think. Well, no, before I go to Slack to see if there's any questions, I should say for those who are here in the Zoom room, raise your hand and I can unmute you, and you can ask your question live if you'd like to do that. Or you can type it in the Q&A panel if that's of interest. But let me just see what questions we have. See, yeah, we have one question here that's asking if you found there were certain types of actions or images that were difficult to recognize, which improved when you used FL at all. I think they're asking if there's some classes that seem to respond to the use of FL.
This is what the kind of work I'm willing to work on, but for now, we have only two classes in the dataset we use, either violent, either non-violent. So the only measure is the accuracy measure. Did we miss? Did we
I
succeed to
see.
classify?
I
There
see.
is no subtypes of violence in these data sets. So
I guess perhaps I suppose this question might have also been kind of assuming, anecdotally, did you notice any errors related to particular, even though the labels are only binary, but when you looked at some of the data, did you notice that some types of errors were, I don't know, associated with a certain kind of action or anything, or maybe?
um, the because one of the data sets was like acted violence, and the others are natural violence. One is from the hockey fields, and the other are from the street, etc. Natural scene. The acted
Hmm.
violence is the more difficult to classify, in fact.
Oh, the active violence, interesting.
Yeah, I
Um,
don't know what's
yeah,
behind that.
yeah, that's interesting observation though. Yeah, let's see what else we can see here. Oh, yes. So another question is, have you looked at self-supervision, and do you think that that might play a role in your research moving forward?
If I have looked into self-supervision,
Yeah, this is the method that is able to leverage um, unlabeled uh, content.
no, I haven't, and I would be interested to. I will search for this. Thank you for the
Yeah,
prompt.
I guess someone's just suggesting a method here. That's interesting.
Mhm.
Um, I guess, I mean, I guess I can ask a question on behalf of myself. You said that you're open to doing work with PhD students and different kinds of work to extend it further. Um, were you thinking that people might join your lab to do this work, or were you thinking more collaborations between other
Ye-
labs out there, or what sort of thing would you prefer?
In fact, yes, I'm thinking more of a collaboration. We very promote collaboration in our engineering school.
Hmm.
I proposed in fact, the French police published a call for projects of interest like this, and we fitted very well.
Hmm.
But unfortunately, we didn't manage to convince the police to the interest of they were convinced of the interest. This is very obvious. Everyone is believes in this interest, especially that we have the Olympics in
Sure,
few
yes.
days. But
Yeah.
the problem is not here. The problem is it is very hard to convince the police to share the surveillance data. This is a very difficult topic. They
Hmm.
would not easily share the data. So, but in general, we are hanging on and we are continuing. And yes, we are seeking collaboration, maybe PhD student between two organisms, between two universities, uh, double financing, etc. It would very promote this research topic.
I see. Yeah, great. Well, I think that's all the questions we have. Thank you so much for joining us today.
My
It's been
pleasure.
a great talk. I think we've learned quite a lot about a new exciting domain that really aligns so well with the fundamental kind of work that people are so interested in the community. So, yeah, thank you so much for joining us.
Thank you, Nick. Welcome.
Let's move on to our next talk. Our next talk is going to be by Adway. He is a software engineer at the University of Maryland. He is also going to speak to us about work that was recently presented, I believe, at a CVPR workshop on data curation and augmentation in the domain of medical imaging. And then this work was so well received, they awarded it Best Poster. So congratulations. And yeah, we were just sort of, when we saw this again would be a wonderful piece of work to share with the community. People can learn from it, maybe get their own ideas about what they possibly could achieve. And so congratulations, Adway, and it's been a pleasure seeing your progress over the last few months and so on. Yeah, over to you. We're really happy to dive in and see what's been going on.
Wow, thanks so much. Thanks so much for the introduction, Nick. I really do appreciate it. Um, yeah, it's been my pleasure and privilege to be presenting our work today. And so, so first of all, can you see my screen? Is everything okay?
Yes, looks great.
Okay, awesome. Yeah, first of all, again, thank you for this opportunity and for inviting me to talk today at the Flower Monthly. This is really a great moment because I follow Flower Monthly, and it's really great to be sharing our work here today. And so, just a quick intro about me. My name is Adway Kanhere. I am a software engineer at the University of Maryland School of Medicine. I develop algorithms for particular clinical translational applications in mostly radiology. And today I'll be presenting one of the papers that I presented at CVPR on privacy preserving 3D medical image segmentation. And also I'll be talking about our participation in the FlowerNext pilot program and the progress that we've made, and just sharing this with the community, and hope that more folks can come in and help develop using Flower amazing techniques for different applications. And so the agenda for today, what I'll be going through is I'll start off with the background and current challenges in the medical domain. And then we'll look at FL as a unique solution, why we can use federated learning in this particular setting, and then some challenges in applying FL in medicine. And then I'll talk about our work, which is Segwis, which will be presented as a paper and as a poster. And I'll also be talking about our work with Flower and how we developed Segways and moved that from a research to a production ready system. And then we'll talk about future scopes. And we also have a short demo. It's not a live demo, but we have a short demo. So I'll also go over how anyone can sort of implement the pipeline that we've developed. All right, so to start off, let's talk about, in general, the two big pillars of deep learning, which is data and models. And so this is, again, very crucial in the medical setting, where data curation and availability is a big concern. So I'll be talking specifically today about medical image segmentation, because that is the most common clinical application in most cases, in most medical applications, has several downstream cases as well. The problem with data curation and sort of using data in a medical domain is that sourcing training data to even develop these algorithms is hard, even though medical data is plentiful and easily abundant. And so we have these sort of three V's that we're sort of dealing with in terms of data curation and availability. The first one is volume. So we have large amounts of data, but that needs to be manually annotated, and creating these annotations is expensive and time consuming, because radiologists have to sit down, or clinicians have to sit down and manually annotate these images. And that takes a lot of time. The second concern is variety. So imaging data is non-IID and heterogeneous. And so what that means is, imaging data coming in is usually at a particular site and using a particular scanner or a particular protocol, and that may be different from site to sites or hospitals to hospitals. And so the other concern is veracity. What that means is images have different views. So some scans are full body scans, so they will have the entire body scanned at one go, or some scans can be specific to a particular organ of interest. So you could have a brain scan or a scan of the abdomen. And the last concern is if you have data already annotated, manually segmented, clearing that data is also a concern because it has, there's a lot of legal and privacy concerns involved, especially around sharing sensitive medical data between institutions. And so this is one of the main concerns for the data. In terms of algorithm development, because our data is so scarce and usually annotated for a particular use case, it's usually annotated with a particular organ of interest in mind. And what that leads to is it leads to models that have a narrow focus. And what that means is it will only be annotated for one particular organ, and it seldom can be used for something else. And what this leads to is that you end up training several models which are trained on the same data, but they're trained for different tasks. And this just decreases the clinical translatability and usability of the data and the models that we're dealing with. So the next obvious question is, do we have a solution that can collectively aggregate knowledge from different tasks into a single unified model that you can use to perform all the tasks together? And that brings me to the next chapter, which is FL as a unique solution. And so the answer is yes. Federated learning is the perfect solution for this problem. And so the idea is that you don't want to share the models instead of sharing. So you don't want to share the data. Instead of sharing the data, you would rather share the models. And this can be a really powerful tool because not only will this allow collaboration between different hospitals and research institutions, but this will also allow companies to come in, work with downstream applications without the need to share the data. And so I'll be talking about some challenges in applying FL in medicine. And so this is great, but like let's look at some particular concerns about why this is hard in the medical domain. This is not a straightforward or trivial solution. And the problem with that is because of the problem of incomplete annotations. And so, like I mentioned before, usually when a clinician will come in, they will manually annotate only a particular organ of interest in the data. And so what that means is you will have sites with like different sites, each containing probably the same field of view, so the same organ of interest. So the same field of view, but different organs of interest, and only one organ will be annotated. And so when you're doing federated learning, this can be sort of explained as a client heterogeneity because clients are working with similar data in the same field of view, but they don't have annotations for the other organs typically that you would see in a centralized setup. And some FL specific challenges that also sort of is a concern is firstly, we have distribution shifts which degrade performance. So in traditional federated learning setups, we've seen poor generalizability when you have client heterogeneity, which means clients usually have completely different tasks that they're training on. And we had a paper from Zhao et al., which showed that the difference in data distribution can have such an adverse effect that it can lead to a drop in accuracy by up to 55%. This is for the global model when we're training the global model of the server. The other concern is, again, the global model itself fails to converge in most cases when the data is non-IID. And it's really hard to get a single global model that can effectively aggregate knowledge and have knowledge of different tasks. And in most cases, what we've seen is most global models, they will have good performance on tasks from a particular client, but might fail or perform poorly on tasks from other clients. This is also something that we've seen when we were doing our research. And I'll talk a little bit more about in the next couple of slides. And then the last concern that we've noticed is, the server requires the knowledge of all the tasks before training begins. So there's no way for new clients to come in and join the federation with completely new tasks or new data. And this sort of limits, again, the real world usability or translatability of even FL. We wanted to allow for effective collaboration with clients. And the other concern is that clients, when you have clients with completely different data, you need to have an optimum model training strategy to be able to ensure that the global model doesn't overfit or individual local models don't overfit or underfit during training. And so I'll be talking a little bit about our solution. So what we've seen, and so our motivation for the paper was we noticed that there has been a lot of research around federated learning with non-IID data. Particularly, we've seen a couple of techniques like we have FedBN, which does local batch normalization, and that has shown to be effective in creating in basically combating this problem of data heterogeneity. But we've noticed that it doesn't it leads to more personalized approaches and doesn't lead to a global model which can be trained effectively. And so there was a seminal paper, which was in ICML 2020, which talked about the convergence of Fed average on non-IID data. And the TLDR from that paper was, if you want Fed average to converge on non-IID data, you need to have some sort of dynamic weight decay. And so we were interested in this technique, and so we went to investigate on that. And so what we ended up doing was we ended up collecting data which is openly available, which is open source data from the medical segmentation decathlon challenge, and we set up this data at 4 different clients. And so we looked at, for example, the liver, spleen, kidney, and pancreas data set, and we chose the modality as the CT or computer tomography images. And we had a completely different test set, which was the beyond the training world BTCV data set, which we chose as an external out of distribution data set to test our model on. And so basically from this table, what you want to look at is notice how every data set at the client has a different shape and different spacing, and also a different sample size. And so this was again a non-trivial problem to actually ensure that federated learning would be able to effectively aggregate this knowledge because of just how heterogeneous this data was. And so what we did was we developed a solution called Segways, which works with heterogeneous data. And some of the techniques that we implemented based on prior research was we had selective weight aggregation using a cosine annealing decay function. And so we also implemented selective weight aggregation. And what that means is instead of Fed averaging, which will ideally aggregate all the weights of the model, we only aggregated particular weights of the model, will be called as representation block weights. And so we split up our usual backbone, which was a 3D UNet backbone, which we use for segmentation, and we only aggregated, say, all the layers except the last 2 layers, which we deemed as a representation block. And the last 2 layers, which were the task-specific blocks, were allowed to train to allow for local model convergence. And so this is an example of a setup that we did. Effectively, we had 4 different clients. Each client will have an individual data set that they're working on, that they're training locally, and then model updates are sent to a global model at the server location. And we implemented the selective weight aggregation and cosine decay. And because of the setup, our setup actually allows new clients to join the federation without the need to even have task-specific knowledge beforehand. Because as training is happening, you could have new clients join the federation and have new tasks that are happening that are being trained on. And because of the way that we designed the model, the UNet backbone, which is only the representation layers are being aggregated, you can change effectively the task-specific layers of the global model, which will allow for new tasks to be trained on as you're going through it. And so the experiments that we ran in the setup, so we ran 4 different experiments. And so as you can see on the top left, the A is the baseline models. And what that means is we trained individual models, single models for each task. And so this will be the sort of like a baseline approach in case you didn't have FL. The second technique was a centralized approach, wherein we aggregated all the data in one location. And remember, we didn't actually have, we still had incomplete annotations. So it was still like a partial label case because not all of these data sets were labeled for all the different organs. And then the third technique that we used was just conventional, traditional federated averaging, where we aggregated all the weights of the model at the server's end. And then the last approach was Segways, wherein we had selective weight aggregation, which was only aggregating the layers of the representation block. And so what we saw was very interesting. And so what we noticed was from this table, as you can see, Segways clearly outperformed all of the other techniques in most cases, in most organs even. And so I'll be going in detail about that a little bit. But from this, you can see one thing to note is that notice how in central aggregation, the central aggregation model actually fails for some organs. And so I'll just be talking a little bit about that too. And so when we look a bit more in detail about the results, what we noticed was with lesser nodes, Segways clearly outperforms or performs at par with conventional FL. And as we increase the number of nodes, Segways outperforms all other setups, effectively demonstrating effective knowledge transfer or knowledge aggregation. And so this is actually really powerful, because what this means is because as you increase the number of nodes or the number of clients, you're effectively allowing for just the selective weight aggregation is allowing for a stronger knowledge transfer, which is leading to better results. And again, central aggregation fails in the setup because your data is so heterogeneous that the partial labels degrade the performance significantly. So when you look at this at an organ level, again, Segways outperforms all the approaches for all organs except the pancreas. And as you can see, we notice it doesn't perform as well for pancreas, and that probably can be because the structure is just so small in general, and it's a very complex organ when you're segmenting it, that even when you're training the baseline models for this task, you don't really see a high performance. So going back, as you can see here, compared to all the other organs, in the first row, the single data set models, pancreas performs about okay, not really the best model. Not really a high dice score. And again, this is the dice score comparison, which is basically just the overlap between the masks and the ground truths, which is a common metric that we use in medical image segmentation. And so again, what we noticed was central aggregation again clearly fails because when annotations are missing, the model just failed to segment some particular organ. So in the 2-node setup, it failed to segment liver. In the 3-node setup, it failed to segment liver and pancreas. Spleen. But we also notice here that clearly Segways has been consistently performing better than even conventional FL in this case. And when we tested this on completely out of distribution data. And so it's even in that case, Segways clearly is performing much better. And so when you look at qualitative results, this is what we see. So notice that in the second in the sample. So I'll talk a little bit about how this is organized. You have your CT image, you have your ground truth, which is what the radiologist will come in and manually annotate, and then you have the results of the different models. And if you look at the first couple of samples, you can see they perform almost really well, but you can see how Segways actually perform slightly better than in your traditional FL setup. And when you look at the pancreas, which are in red, what you can see is if you look at the fourth option, the fourth row, you'll notice how Segways is the only one that actually approximates a small region of the pancreas. It's because, again, that's such a complex organ that it takes a lot of data to be able to train that really well, and all the techniques just fail. And if you look at the central aggregation, again, you'll notice that central aggregation just straight up fails to segment particular organs in most cases. So this was all great. So now this is the fun part is how can we implement this in a real-world setup? And that's exactly where Flower comes in. And we've been super excited about this, and really it's been great to work with Flower to sort of move our research paper from the research paper to actually see if we can make a production level unit. And so this is what the Flower Federation looks like. And so again, this is Flower 1.9 ready. We're really super excited about seeing how we can improve on this. But effectively, what the Federation looks like is you have your superlink, and your superlink is going to coordinate between your servers and your supernodes, which are clients, the servers that join. And will be again linked to the servers already available. And you could start. You could say you have a server which is part of your research organization, and you're connected to different clients. Again, using SSL encryption, which is again provided by the Flower API for Flower 1.9. you can connect to the Superlink and start training and be a part of the federation. But say you want to now share your models or the tasks that you trained to a new research lab. And so all you would have to do is as simple as just sharing your certificate with the other institution, and they can connect as a new server. And when they do that, they will be able to download the best trained global model at the Superlink, and then if they want to have their own set of clients, they'll be able to add in and support training for new tasks as well. And all of this will happen while you already have a federation of supernodes and servers already training and training on different tasks. And so, this effectively shows that you can have clients add and join and even drop, and also completely work with heterogeneous data at scale. And so this is the demo that we presented at CVPR. This isn't a live demo. My apologies, but feel free to scan the QR code, and that will lead you to our GitHub. I'm just going to be talking about what are the steps and how easy it is to set this up yourself. And so again, all you have to do is just clone the repository, and you can have your environment set up. We've created a requirements file, so all you have to do is just install the requirements, and you should be good to go. And once you do have that, you can download the data sets. So in this case, we've shown the screen and the paper. So this is because they're pretty small, they're easy to download, and you can run this on a system that doesn't require too much compute. And once you have that, what you can do is you can run this experiment in a centralized setup, which is again talking about the centralized model that we trained, or you can run Federated with the Federated API. And in this case, we actually show that we don't really have the SSH certificate case, but again, there's documentation to do that. We will be updating the GitHub repository to add instructions on that as well. But effectively, what you'll do is you'll start your Superlink, and once you start your Superlink, and you can have clients which are training for a particular organ, and you can start those clients and connect that to the Superlink and begin training. All right, so let's talk about the future scope. So we're really excited, how this has all come together, and we really would like to continue working on this. And so what we're going to do is we're going to add support for more models. So in the medical imaging segmentation community, a more common model to use, or a common AutoML technique to use, sort of AutoML for medical image segmentation, is NNUnet. And so we're looking at how we can sort of increase the scale and make this completely model agnostic. And also extend segues to clients with multiple modalities. So for parts of our research paper, we only chose CT images, but we also want to extend that to clients that will probably be bringing in magnetic resonance images or X-rays, and see how all of them can still be a part of the federation, and provide a global model that should be able to segment all of this together. One of the concerns that we noticed was standardizing the data. And so when you do have data heterogeneity, a big concern is how will you standardize the data that you're loading in, especially when you have such variety of data, you have 2D and 3D data. And so that's also something that we're interested in doing. So the way that we're probably envisioning this is that we'll have a common data format. So irrespective of what modality and what data you have, you should be able to connect that effectively. And then we also want to investigate the performance of the global model as and when clients join and drop the federation, to ensure that you're actually training a global model which doesn't have problems with performance degradation as clients drop or join. And so, yeah, if you're interested in reading our paper, again, like they said, we just presented this at the DCAMI workshop at CVPR, where this was awarded the Best Poster Award. We're really excited, and if you do want to check it out, we highly recommend you read our paper, and you can get more information about how we've implemented this from a research perspective. And so, again, thank you to all the friendly folks who made this possible. I just want to have a special mention to Nick. Thank you so much for having us as part of the Flower pilot program. Special shout out to Javier, who's been super supportive and helpful in sort of building this infrastructure with us. And then to Vishwa Parekh, who is my PI, and who's the lead PI on this project. And also to every team member here at University of Maryland who helped this, with Dr. Paul Yi and Sana Kulkarni as well. So thanks to everyone who really made this possible. This is not a one-man show. And thank you for your time for tuning in and listening to this. If you have any questions or comments, I'd be more than happy to discuss.
Great, thank you so much. It was really, really interesting on, I think, multiple fronts. It was interesting on the front of research, and also on the front of showing people how they can take some research idea and kind of make it a little bit more production-y and moving it forward towards actually deployment. Fantastic. Just as we did with the other talk, if anyone in the room wants to ask a question, just raise your hand. I won't mute you, or you can use the Q&A facility here, or I'll look around to see if I can find other questions from folks in Slack and other places they can submit them. Let me see what I can find here. Oh, I see. Organ labeling. There's a question. I think it must refer to early on in your talk. They were asking a question: Is there a standard for labeling this organ data? Yeah, I said often this happens. People have different institutions labeling information differently. That can make the learning more problematic. So, in your domain, is that well established, or how did you deal with the problem if there was a problem?
Yeah, so we do have standardized formats for working with these images. So DICOM is the most common one used to use those, but there isn't necessarily a standard technique of doing this. This varies from clinician to clinician. So you could have some clinicians go above and beyond and literally segment every slice when you're going through it for these images, or you could just sort of segment a bunch of slices and then sort of extrapolate that to fit the entire organ. And you also have auto segmentation tools that some institutions will end up using to sort of help with the segmentation process. So it's really not standardized per se. There still is a standard format, but you can still see differences in labeling. And that is actually a big concern because, if you don't have, as for any machine learning model, if you don't have clearly labeled data, that is going to affect your performance. And so we've tried to sort of develop tools that will allow clinicians to segment this in a better way. You have a lot of open source techniques, open source tools that a lot of institutions use. But again, this is not something that's completely standardized.
I see. Interesting. Cool. Yeah, I see there's another question about there was, I guess it's about organ variation. There was accuracy shown where there was some variation in accuracy with respect to organs. And the question is, do you know why that's the case? And see here the person put like, is it the size? Is it the number of pixels? Is it something else?
Yeah. So I think I'll just share my screen again to sort of read through that. Yeah, so what we've noticed is that it definitely depends on the size of the organ. So if you can look at the table here, again, like I said, the pancreas is sort of a smaller organ, a lot more complex. When you're looking at these images, you'll notice that when you're segmenting them, you'll notice how the view changes as you go by. For big organs like the liver or the kidneys or even the spleen, I would say the spleen is like a medium-sized organ. For bigger organs like the liver and kidneys, you see much better performance. And so that's why you see higher numbers in almost all cases. Whereas for the pancreas, you see that just because of the complex nature of how the organ is visible in the image, and also because of how small it is, you see not that great of performance.
I see. Interesting. Yeah, because it's reasonably pronounced in some cases here, depending on the organ and the number of nodes and the technique being used.
Yeah. So another thing I think just adding on to that is that we've noticed when you have multi-client setup, so for example, the 3-node and the 4-node setup, if you look at the 3-node setup, it actually is kind of counterproductive because the central aggregation technique completely fails to segment the liver and the pancreas together. but ends up somehow segmenting the spleen. And even for the 4-node setup, it ends up actually doing the exact opposite, when it doesn't segment the spleen at all. It just ends up probably segmenting the other organs. And so again, we feel that this is just because of how heterogeneous the data is. That bigger organs will be easier to segment, but when you're collectively training this and putting them together, that's really when it degrades the performance. And so just to add on to that, when you're training this, FL probably does a really good job of training this because of doing this in a decentralized manner, wherein you actually have, because you're doing this the knowledge transfer at the server, it's kind of like the server is able to see different organs separately, different views, and able to aggregate that knowledge effectively, which probably central aggregation is not being able to do.
Right, I see. Interesting, cool. Well, the one last question I actually had myself was that with your demo code that you showed, is it possible to can people use that code to stand up a very similar system but then change out the task? Or is it more just a demonstration of what you showed us so far?
Oh no, definitely. So this code is completely modular, and you can change it to have any task that you want. We designed it specifically for medical imaging, and so that's why you see this. And because of we wanted to test out the research that we did in our paper. That's why I showed today with the data set that we used for a research article. But you can use this. You can change the algorithm backend, so you could change Fed average, and you could try some other technique. And again, because this is supported completely with Flower 1.9, it's as simple as changing just a single line of the server to change the aggregation strategy. But you can also change the data sets. And so all you have to do is just probably for now, all you will have to do is just go into your client app and provide techniques to pre-process that data. So we're still working on that. So we're going to try to make it, again, completely agnostic. You would just have to feed in your data set and probably just give in particular variables, like, what is my intensity values for these images? And you have the script do this automatically. But for now, you just have to load in your data set and then give it certain pre-processing techniques that you would like to do. And then you'll be able to launch the client.
I see. I got you. Yeah, it makes sense. That was what I kind of had in mind. But yeah, okay, excellent. Oh, I was going to end things, but I see we have two other questions, so let's take them. One question is written down here. It says, "Great talk. I was just interested if there was a specific reason in choosing a multi-head unit encoder for the task. Given the multitask nature of the task, I was curious if something like an MOE will be better suited for this application, or was the intention to create a single, more lightweight expert for organ segmentation?"
That's a great question. Yeah, so I think the intention was to sort of make a very lightweight model, and so that's why we ended up choosing a mono unit at the back end, just because it's really modular, and we ended up choosing the multitask approach because of that. But yes, you could try different techniques. You could try a completely different backend, and that's something, again, we're interested in seeing. And so we're actively working on the next steps to see how this would work with a completely different backend. But again, we chose the unit because that's just such a common technique in segmentation. That's usually the first default go-to technique that you would use. And so that's why we ended up using that. And also another concern was sharing these weights with the global model. We know that there's significant overhead when you're sharing this, when you're communicating with the central server. We wanted to reduce that, and that's also why we chose a simple unit in this case.
Got it. Sounds good. Let's take one more question. This is from Sanjeev. I'm going to allow him to talk, and he can ask his question for himself. That's great. So Sanjeev, you're online.
Yeah. Hey, great talk. One quick question is, you mentioned selective weight aggregation. Can you just re-summarize that? And also, I mean, were these all weights in a one particular layer? How, are there some sort of known statistical techniques for identifying sort of the best selective subset of weights to aggregate, or whichever are affecting the gradient the most, or so on, right? So can you sort of, how generalizable is that if we wanted to do selective weight aggregation for all kinds of applications, possibly including generative AI applications? So just kind of more context on sort of the basis behind the selective weight aggregation.
Got it. Yeah, that's a great question. Thank you. Yeah, so for this study in particular, what we did was we empirically determined what would be the weights that would be important for being part of the representation block and those being part of the task block. And so based on our analysis, we realized that at least we wanted the UNet to have a good enough amount of encoder information while still being able to generalize and make personalized FL. And so that's why, again, this was all empirically determined. But yes, you do have smarter, intelligent strategies of how you can go about selectively aggregating the weights. What we usually see is you could also look at, say, running experiments wherein you would create a sort of sampling strategy, like to select which weights would be important, and then you would be able to run some sort of any sort of statistical technique to sort of verify. We haven't tried this, we haven't done this really, so but that's I think an avenue that we can definitely look into. I think it's really important. You could also try something like a core set, for example, to determine what would be the effective size that of the layers that you would want to aggregate. And yeah, I think that's what comes to my mind. But I hope that answers your question.
Oh, great. Well, thanks for that final answer. We're running a little short on time, so I'm just going to move on. Thank you again for the great talk. Let me just reshare my screen here, and we can transition to the end. And that is to say, thank you everyone who's attended. Thank you to Adway. Thank you to Siba for the wonderful talks. And we will be back for Flower Monthly August. As always, first Wednesday of the month, and that corresponds to August the 7th. Again, 1600 UTC. And if you're interested in letting us know how we can improve Flower Monthly, please join the Slack channel, where we have a dedicated one just for Flower Monthly. If you want to make sure that you're kept up to date about upcoming events such as Flower Monthly, but others, you can subscribe to our calendar. And again, yeah, thank you all for joining us. It's wonderful to always see you all here. And take care for now. Bye-bye.
Bye-bye. Thank you.
Thank you, everyone.